Hello, this is Unit 4, Lesson 6, Part 2 of the homework. I've had a question about number 36. Find the volume of the largest cylinder that can be inscribed in a sphere. So, let me start by drawing myself a sphere, and then I'm going to inscribe, go to a different color, a cylinder. So the cylinder will look something like this. Did it right? So we got a cylinder inside the sphere. Here is the middle of the sphere. What information do we know about a sphere? Well, the only piece of information you ever get from that is the radius. However, and this is a habit you got to kind of break. Although that's how we normally draw the radius, it's not very helpful. All right. We need to draw the radius in a way such that it relates to the cylinder. So what I'm going to do is I'm going to draw the radius to the point where the edge of the cylinder touches the sphere. So that also is a radius. And now I've made a connection between the sphere and the cylinder itself. Okay? What else do I know? Well, the cylinder, we need a radius. I'm going to use small r for it, capital R for the sphere. And I need to know the height of the cylinder. So this is where things get interesting. So the constraint equation here, we have to draw a relationship because we want to optimize. At the end of the day, we want to find the largest cylinder. So the volume of a cylinder. So this is my optimization equation. Volume equals pi r squared h. And r is small r for the cylinder. So the constraint equation has to draw a connection between the sphere it's contained in and the variables in play. So when I draw it like this, we can start to see we're going to end up using Pythagorean theorem because I have a right angle triangle. The only difference is that this length right here doesn't represent the full height. This is only half the height. So now I can draw a connection between the two. The radius of the sphere squared is equal to the radius of the cylinder squared plus half the height of the cylinder squared. Excuse me. Now, again, I like what I see because I have a small r squared that I can play with. And this is the other part. Just give me 1 sec. I'll rearrange it. So small r squared equals capital R squared, so that's your sphere, minus 1/4 h squared. Okay, so I've rearranged it. Now, the question I always get in class now is, well, it's not going to work. I have too many variables. You have to remember that this guy right here, the capital R for that sphere, it's a constant. Okay, we're adjusting the size of the cylinder, so the radius and height is changing in the cylinder, but our sphere is a constant. It's not changing its shape. All right, so it's just a number. It could be a radius of 5, radius of 6. It's not going to change. So technically, I don't have 3 variables. I only have the 2. So when I make the substitution into the optimization formula, I get pi. Replacing r squared, I get capital R squared, which is just a constant, minus 1/4 h squared h. The volume equals pi r squared. I'm going to put them together. Again, that's just a number times h minus pi by 4 h cubed. All right, and the pi by 4 is just a number. So I just have power rule here. So if I take the derivative of volume with respect to the height of my cylinder, I end up with pi r squared minus 3 pi by 4 h squared. If we let the change in volume with respect to height equals 0, 0 equals pi r squared minus 3 pi by 4 h squared. Excuse me. Pi's will cancel out. Simplifying, we find that 3/4 h squared is equal to the radius of the sphere squared, h squared oops, equals 4/3 capital R squared, or take the square root of everything there, 2√3 capital R, or if I multiply top and bottom, if I rationalize, the height of the cylinder will be 2√3 over 3R, and I believe it's just in units. So there we go. That will be the height of the cylinder, and we want to know, find the volume of the largest cylinder. So we need to find a volume. So I need to find the radius. So I go back here, my radius, R squared equals capital R squared minus 1/4. And here's a little bit of a trick. I'm replacing h squared. So if I look at my previous work before I simplified, there's an h squared already. So I know h squared is equal to that. So that saves me a little bit of work. So it's 4/3 capital R squared. 4's cancel. So I get small radius squared equals R squared minus 1/3 R squared. So R squared, or my radius, is equal to 2/3 capital R squared units. I'm not going to bother simplifying because, again, my ultimate goal here is, what is the volume? Volume equals pi R squared H. Well, I want to know R squared, so there's no sense going any further with that. I know my H. So volume equals pi 2/3 capital R squared multiplied by 2√3 over 3R. So that means that the volume will be, let's see here, so I have 4 pi √3 over 9 R cubed. I think I covered everything there. Go back up to the top, 4√3 pi, looks like matches up. All right, there we are. I think there is a typo there. This should be cubed because I don't see where I lost that R, so I think I just did a typo in my answer there. All right, so therefore, optimal volume of a cylinder in a sphere of radius R is 4 pi √3 R cubed over 9. All right, definitely a challenging question. It's really just finding what's the optimal dimensions of the cylinder. They just ask you to come up with the final volume. If you have any questions with that or want further explanation, let me know.